Today in this lecture we are going to discuss the singularities and their classification. So first of all I want to define zero of an analytic function. A zero of an analytic function fz is a value of z such that fz equal to 0. For example, if fz equal to z minus 2, then 0 of fz is given by f of z equal to 0. This implies that z minus 2 is equal to 0. This implies that z equal to 2. Hence, z equal to 2 is 0 of fz. Second, I want to define 0 of order m. An analytic function fz is said to have a 0 of order m at a point z equal to a if fz is expressible as fz equal to z minus a power m into phi of z, where phi z is an analytic function and phi of a equal to not 0, For example, if fz equal to z minus 2 power 5 into z plus 3, then z equal to 2 is a 0 of order 5 for fz, because here z minus a power m into 5z, here a is 2 and m is 5, and this function phi z, that is z plus 3, is an analytic function, and phi of 2, this is equal to not 0. So z equal to 2 is a 0 of order 5 for this function fz. Note, a 0 of order 1 is known as simple 0. Next, I want to define the singularity. A point z equal to a is said to be singularity of a function fz if fz is ceases to be analytic. At that point, for example, if fz equal to 1 upon z minus 1 into z plus 4, then z equal to 1 and z equal to minus 4 are singularities of fz, because here the point z equal to 1 is the singularity of fz, because at this point the fz ceases to be analytics, and also z equal to minus 4 is the singularity of these functions, because at this point the function ceases to be analytics. Next, classification of singularities. There are two types of singularities. First is isolated singularity. And second is non-isolated singularity. Isolated singularities, there are three kinds. There are three types of isolated singularity. First is removable singularity. Second is pole. And third is essential singularity. A point isolated singularity. A point z equal to a is said to be an isolated singularity. Of a function fz if first fz is not analytic at z equal to a, and the second fz is analytic in the deleted neighborhood of z equal to a. For example, fz equal to 1 upon z minus 3 into suppose z plus 4. Here z equal to 3 and z equal to minus 4 are isolated singularity of fz. Because if we consider fz equal to 1 upon z minus 3 into z plus 4, then z equal to, then the function fz is not analytic at z equal to 3, and here fz is analytic in the deleted neighborhood of z equal to 3. Similarly, fz is not analytic at z equal to minus 4, and fz is analytic in the deleted neighborhood of z equal to minus 4. So z equal to 3 and z equal to minus 4 are the singular isolated singularities for fz. Next, consider the Lorentz series. Fz, this is equal to summation n equal to 0 to infinity an z minus a power n plus summation n equal to 1 to infinity, here bn z minus a power minus n say this is equation number first. Here this part summation n equal to 0 to infinity n z minus a is the analytic part, and this part summation n equal to 1 to infinity b n z minus a power minus n is a principal part. So analytic part is this part is said to be analytic part, and this part is said to be summation n equal to 1 to infinity b n z minus a power minus n is said to be principal part. Now I want to define removable singularity. If the principal part of fz contains no terms, then the singularity z equal to a is said to be removable singularity. Is said to be removable singularity of fz. For example, fz equal to sin z divided by z has a removable singularity at z equal to 0. Solution. Here fz equal to sin z by z. This may be written as 1 by z. If we expand the function sin z, we get here z minus zq upon factorial 3 plus z power 5 by factorial 5 minus and so on, and this gives 1 minus z square upon factorial 3 plus z power 4 upon factorial 5 minus up to so on. This may be written as 1 minus here z minus 0 का whole square upon factorial 3 plus z minus 0 power 4 upon factorial 5 minus up to so on. Here we see that the principal part means negative powers of z. Here the principal part of fz contains no terms. That is no negative powers of z. So z equal to 0 is a removable singularity for fz equal to sin z by z. Next, I want to define pole. If Bn equal to 0 for n is greater than m, that is principal part of a object contains finite number of terms, say m, then the singularity z equal to a is called a pole of order m. So fz becomes summation n equal to 0 to infinity, here an z minus a power n plus here the principal part which contains m terms, so we write summation n equal to 1 to m, here bn z minus a power minus n. If we expand this series, we write summation n equal to 0 to infinity, here an z minus a power n plus b1 upon, if we put here n equal to 1, so we write b1 upon z minus a plus b2 upon z minus a का होल स्क्वायर प्लस अप टू सो वन प्लस बी एम अपॉन जेड माइनस ए पावर m, or the second definition of the pole is a function fz is said to have a pole of order m at a point z equal to a, if fz is expressible as fz, this is equal to phi of z divided by z minus a power m, where phi z is analytic function and phi of a equal to not 0. For example, fz equal to 1 upon z minus 2 का power 3 into suppose z minus 5 power 4. Here z equal to 2 is a pole of order 3 and z equal to 5 is a pole of order 4, because fz can be written as 1 upon z minus 5 power 4 divided by z minus 2 power 3, which is a form fz equal to phi of z upon z minus a power m. Here phi z equal to 1 upon z minus 4 power 5 is analytic, and phi of a, that is phi of 2, this is equal to 1 upon 2 minus 5 power 4, this is 1 upon minus 3 power 4, this is equal to 1 upon 81, which is not equal to 0. Similarly, we can say that z equal to 5 is a pole of order 4. For the function fz. Next, I want to define essential singularity. If bn equal to not 0, for infinitely many values of n, that is principal part of fz contains infinite number of terms, then the singularity z equal to a is called an essential singularity. For examples, if you consider the function fz, this is equal to e power 1 by z, has an essential singularity at z equal to 0. Because fz, this is equal to e power 1 by z, by the expansion of e power 1 by z, we write 1 plus 1 upon z factorial 1 plus 1 upon z square into factorial 2 plus 1 upon zq into factorial 3 plus up to so on. This may be written as 1 plus here z minus 0 power minus 1 upon factorial 1 plus z minus 0 whole square upon factorial 2, here z minus 0 power whole cube upon factorial 3 plus up to so on. So this power is here negative, this power is also here negative. Here we see that the principal part of a object contains infinite number of terms. So z equal to 0 is called an essential singularity. For fz equal to exponential of 1 by z. Note, first, limit point of poles are called non-isolated essential singularities. And second, limit point of zeros are isolated essential singularities. Third, removal singularity due to Riemann if z equal to a is an isolated singularity. Of fz, and if fz is bounded and some deleted neighborhood of A. Then A is a removable singularity. Theorem. A rational function has no singularities other than poles. Proof. Suppose fz is a rational function. So that it is expressible as fz, this is equal to phi of z upon psi of z, where phi z and psi z both are polynomials. Having no factors in common. Singularities of fz are given by psi z equal to 0, that is by zeros of psi z. But zeros of psi z are poles of one upon psi z. Finally, singularities of fz are poles at the zeros of size z. Hence proved.